Okay, so this is problem 2.6. And problem 2.6 wants us to find the electric field a distance z above a center of a flat circular disk of radius r that carries uniform surface charge sigma. So you may say this is pretty much the same thing as the last problem we did, but there's a difference. And that's the fact that we have surface charge sigma. So as before in the previous problem, if I pull it up, this was just, you could think of it like a ring. The difference here is this is no longer like a ring. This is an actual circle, like filled in circle, I guess you could think of it as. So I just drew a picture, a point P above, and the big difference is now we're going to have to integrate through this circle here because of the surface charge density. Now, just like before, we said that there would only be an E field in the Z direction, and that's still true. So our E field is going to be 1 over 4 pi epsilon naught, the integral dq script r squared times cosine theta. And this is because it's only in the direction. Okay, so if we drop this here, 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 this is z, this is x, this is theta. We only want the cosine, so we only get that z component. So that's why we're multiplying it by cosine. So script r squared should be easy to see. That's just going to be z squared plus x squared. Now dq is going to be a little bit different here because now it's a charge, you could think, I guess, per area. So we're going to have our sigma times the 2 pi r, but the r, we're not using capital R because we're not necessarily going to the very end. We're just going to call it x dx. Okay, so if we were to look at the units here, sigma has charge per area, and then we have 2 counts of x, which gives us our area, so we end up just getting our charge back. We're using x instead of r because x is just how far into the circle we're going. Capital R represents the entirety of the circle, but we want to count everything from the very, I guess you could think of as just these little circles that we have here gradually getting bigger and bigger and bigger until we reach the circumference. So that is our dq, and then we need cosine theta, which, just doing some right triangle trig, should be able to say is z over the square root of z squared plus x squared. So then we can plug all that stuff in, and we get the E field is 1 over 4 pi epsilon naught. We're going to integrate from 0 to r. So again, we're integrating from this dot right here. I'll do it in this color. From this dot here until we're at a distance r away. So that's why our bounds are what they are. Sigma times 2 pi x times 1 over, I'm going to combine these guys, z squared plus x squared to the 3 halves, times z times dx. So we can factor out some constants here, and you'll get 1 over 4 pi epsilon naught, which has always been out there, times 2 sigma pi z times the integral from 0 to r, x, that cannot be pulled out, over z squared plus x squared to the 3 halves dx. And you can see some stuff will cancel. The pi, for example, this will become a 2. Now, I'm not going to go through and solve this whole integral. It's just a very easy u sub. If you don't know, you let u be equal to z squared plus x squared. So that du is 2x dot dx, or 1/2 du is equal to x dot dx. So you substitute this as u, this is 1/2 du. So again, the point's not really to prove you can do a u sub. You should be able to do a u sub and whatnot. And if you're not comfortable with that, I did actually work out the full thing in a few videos back. Long story short, you'll end up getting this for your solution according to the computer in the k-hat direction. I should mention that. K-hat, gotta get our direction. And that is essentially our problem. The other thing I want to talk about really quick is just to notice the limit as r goes to infinity of your E field. Essentially what you would get is this will get a bigger and bigger and bigger number until, because your r is growing. So when your r is growing, you're going to be squaring a bigger number, which means you're going to get a bigger number. So you're going to be dividing by a bigger and bigger number. So that number is going to get smaller and smaller because we're dividing by a bigger number. So when you do that, you should be able to see that sigma over 2 epsilon naught is your E field when you're really far away. There was another part, I'm not going to talk too much about it, but it said just check for when z is much greater than r. Essentially what you're going to do is you're going to factor out in the denominator under the square root there, and you're going to create a ratio of z and r. And when z is much greater than r, you're probably going to want z in the denominator. So I'd probably factor a z squared out, so you'll have r squared over z squared, and that term will go to 0. You can do a binomial expansion and get that, but I really just wanted to work on the E field more than anything. So hopefully that helps some people.